Next speaker is Abhay Nayak from the Weizmann Institute. He will tell us about topological superconductivity in OHB tantalum disulfide.
Hi, hello everyone. I hope you can hear me well. Thank you so much for this kind opportunity to present our spectroscopic measurements, where we see signatures of topological superconductivity in a layered transition metal dichalcogenide 4Hp tantalum disulfur. So the measurements were carried out under the supervision of Chaim Weidenkopf here at Weizmann Institute of Science, and the material was grown by Amit Karnigal's group at the Technion Institute. And we have enjoyed very strong collaboration, theoretical collaboration with Yuval and Bingai's group in Weizmann Institute of Science, and with Greg from Northeastern University. So this is the brief outline of my talk. So I will start with a very brief introduction to topological superconductivity, and especially focusing on the experimental signatures that you would expect, and also introduce this material 4Hp tantalum disulfur. Then we'll dive down into our experimental results, where we see strong charge density wave modulations, both on the 1T and the 1H surface of this material. And by further cooling down below the TC, we see this well-developed superconducting gap. And then we will examine the different kind of edges that this 2D state can host, that is the zero-dimensional edge of the vortex and the one-dimensional edge of the step edge, and examine what kind of edge states are associated with it. And I will conclude by briefly talking about the theoretical model, which kind of neatly captures all our observations and describes the origin of this topological superconductivity. So feel free to ask me, interrupt and ask me any questions during the talk if you have any. So we've all seen this wonderful experimental works on 1D topological superconductivity, where we have these proximatized semiconducting narrowires, where we have a bulk gap, and the Majorana bound state sitting appearing as these zero bias peaks at the ends of the nanowire. And this has been observed in several systems by now, starting from the semiconductor superconductor heterostructures, and followed by several other systems like this atomic chain on the superconductor, proximatized helical edge modes of bismuth, and also gold nanowires proximatized by superconductor and a ferromagnet above it. We expect to see some different kinds of signatures in 2D topological superconductivity. So one we have already addressed, that whenever we have a zero-dimensional edge of the vortex, as has been beautifully described by Hong's experiment and the talk just before, they have found these very sharp zero bias peaks, the Majorana zero bias peaks in the center of this vortex cores, which are also even quantized, and has been observed in FESE-TE and some other types of material systems. There is also another type of edge here, which is this 1D edge, and just analogous to quantum Hall systems, depending on if the system is chiral or helical, we can have a chiral or helical counterpropagating edge modes on its boundary as well. There has been some evidence of these Majorana 1D edge modes on some systems. For example, NVIDIA's group, they have also observed in FESE-TE system, there's an edge mode associated with the domain wall. And in other kinds of heterostructures, be it a magnet on top of a superconductor, or even in this chromium bromide deposited on niobium diselenide, there are some signatures of Majorana edge modes on its boundaries. Now, one of the outstanding challenges that still remains for the community is to realize this type of edge modes or topological superconductivity in intrinsic materials, in stoichiometric materials, which are preferably layered, that would allow ready applications into device engineering and do something with it. So towards that end, we study this very novel material of 4Hp tantalum disulfur. And it basically consists of an alternate stack of 1T and 1H tantalum disulfur. Now, the 1T tantalum disulfur is a very well-known Mott insulator, which has very strong charge density wave structure, a reconstruction on its surface. And because this material, to the lowest temperatures measured, does not show any magnetic ordering, it's a leading candidate to host quantum spin liquid phase, and is being studied exhaustively. And on just below this is the 1H tantalum disulfur, which is a prototypical 2D superconductor and shows Ising superconductivity. And there are also many theoretical proposals of realizing topological superconductivity on the surface, either by applying an in-plane magnetic field or by the fact that this material, for example, niobium diselenide 1H polytype, is very close to a ferromagnetic transition. The stack of 1T and 1H also contains more interesting physics than one could get out of just the 1T and 1H. For example, in monolayer MBE grown 1T and 1H tantalum disulfur, there have been reports of a strong zero bias peak that is appearing as the Kondo resonance in these type of systems. Our a project was really motivated by this neat observation from Amit's group, where they did muon spin rotation on this material and found that the relaxation rate of these muons strongly increases as at the onset of the TC, strongly suggesting that the superconductor is in a Brocal time reversal state. And that's the goal really of this project, to study what kind of topological superconductivity or its features and characterize in detail using STM. STM being a local probe is really ideal and suited for this type of measurements of local bound states. So we have these single crystals of the 4HB tantalum disulfur grown in Amit's group. We glue it into our sample stage and cleave it in ultra high vacuum condition. And we bring in a sharp metallic tip very close to the sample, thus allowing us to measure the tunneling current. Now, this tunneling current is exponentially proportional to the distance between the tip and the sample, thus allowing us to measure these topographies with very high resolution. Here is such a topography of the 4HB tantalum disulfur, and once we mechanically cleave it in ultra high vacuum, we can get different surfaces. So for example, here we have the 1H layer, which terminates at the step edge, and the 1T layer underneath it. If we look at high resolution topographies on this 1T layer, we clearly see the different patterns, the small balls corresponding to the atoms, and this large density wave, charge density wave, corresponds to this prototypical square root 13 by square root 13 reconstruction of the surface, the Star of David's created here. And this can be further examined in detail in the Fourier space, Fourier analysis of this topography, where you have the CDW peaks here and the atomic Bragg peaks here. We can do the similar analysis also on the 1H surface, where we see these two different types of patterns. And going to the Fourier space of it allows us to distinguish where the atomic peak is. And interestingly, we see two different types of pattern close to the charge density wave Q vectors. So one, which is this very faint CDW pattern, corresponds to the intrinsic 3x3 CDW of the 1H layers, which is also present in niobium diselenide. But what we see interestingly is there is a very strong CDW peak, which corresponds to the 1T, which is square root 13 by square root 13 CDW peak. And we'll see later that this could have very interesting implications on the nature of superconductivity of the 1H layer. We can also see that the CDW of the 1T layer really falls on top of this 1H layer, suggesting there is a strong imprint of this underlying 1T layer on 1H. So just like topography, after which we can measure the density of states, the electronic structure of this material. So for example, here is the DIDV, which is proportional to density of states measured on the 1H surface somewhere far from the defects as shown here. And it shows a typical metallic spectrum as one would expect when measured at 4.2 Kelvin, which is higher than its TC. Now we can lower down the temperature down to our base temperature of 0.4 Kelvin and zoom in very close to the Fermi energy. And we see that we get a very typical BCS-like spectrum on the 1H surface. If we increase the temperature and the magnetic field beyond its corresponding critical values, we recover the normal state as we would expect. We note that we cannot really fit this BCS-like spectrum to a regular BCS, and because there seems to be an enhanced zero bias conductance more than what could be accounted for by electronic temperature or by the instrumental broadening. And to fit this, we have to use a finite offset plus a BCS. And I will give a better motivation of why we need this when I discuss the theory. For the time being, I'll just use this peak position, the coherence peak position, and refer to this as the gap size. And we'll see how it evolves in space. So this is one of the topographies measured on 1H surface. And we see that there are sometimes these modulations on the 1H. But the superconductivity doesn't really care about it. And that we can check by taking a line cut, that is measuring the density of states as a function of this along this line, as shown here. So the false color is the DIDV as a function of position and energy. And we see that the superconducting gap remains quite stable, even if there are these modulations, large topographic modulations on the 1H surface. Now, one way to create defects in this system is to apply a magnetic field, which creates this vortex. And that we can do by applying a magnetic field out of plane of 100 millitesla, as shown here. And then we measure the density of states at the zero bias energy, shown here in the false color, as a function of position, x and y. And the way SDM sees this vortex core is that the vortex core has more normal states than its outside, and these appear as enhanced density of states. We can also examine what is the coherence length of the superconductor just by studying the decay profile of this vortex core, and it turns out to be 21 nanometers, very close to what was obtained from transport measurements. And we also see that in the background of this very well-ordered vortex lattice, we have these speckles, some kind of impurities, which slightly increases the density of states. Now let's examine the vortex core in more detail. So we take a line cut. So this is the DIDV. It's the false color measured as a function of position. We start from away from the vortex across it, and we measure it as a function of the energy. If we look at the profile, the DIDV profile far away from the vortex, we get this regular superconducting gap. And if we compare it with the spectrum measured right on the vortex core, we see that we have nearly a normal state with a bump, with a zero bias peak-like structure at the zero energy. And let's zoom into it, and we see this enhanced zero bias peak-like structure, which we can fit it to a single peak Gaussian profile. But the width here is larger than what we would get from just a thermal broadening. And this does not, and this system, both with our instrumental broadening and the high Fermi energy of the system, does not really allow us to distinguish the origin of the zero bias peak. So unlike what we saw in Hong's measurements, we cannot tell whether this comes from CDGM states or from a thermally broadened Majorana zero bias peak. And to address this very question of what really is the topological nature of this material, we go on to study the next type of defect, the 1D defect that can be found on the 1H step edges. So here is such a topography. We have the 1H on top, which terminates here along the step edge as indicated in this black dashed line, and the 1T layer that's below it. Let's see what the spectrum looks like far from the step edge. This is what is shown here in blue. We get a regular BCS-like spectrum. But when we measure the spectrum close to the step edge, we see there is a strong enhancement in the zero bias conductance. Also note that there is a small decrease in the gap size, but this decrease in the gap size turns out is not enough to explain why we have this strong increase in the zero bias conductance. And to actually fit this, what we had to do is take the BCS plus a Gaussian profile centered around zero bias peak, and that only allows us to fit this point spectrum measured on the step edge, strongly suggesting that we have this additional edge mode bound to this 1D step edge. To examine this in further detail, let's look at line cut. So we measure DIDV as a function of position and energy, starting far away from the step edge, approaching the step edge at x equals 0 nanometers. And we see there is indeed some enhancement occurring within the superconducting gap. So let's track the position of the coherence peak and what happens to superconducting gap. So it's plotted here. So we see that for most of the region, the gap size does not really change, but there is small reduction in the gap size very close to the step edge. But what is clear is the zero bias conductance increases rapidly, even when the gap size is not changing. We can fit this enhancement of the zero bias conductance to an exponentially decaying model, and this gives us the decay length of the system, which is 18 nanometers, very similar to what we get in the coherence length of the system. So what this means is we extracted the decay length for at the zero bias energy only, and this means that there is some kind of state localized to the step edge within this superconducting gap. We can repeat this same analysis for different bias energies within the superconducting gap, and then just extract repeat the same procedure and extract what is the decay length, and we get a fairly constant decay length. This suggests that we have an edge mode which is not just at zero energy, but probably also has some dispersion associated with it. Now we can also examine how does it behave in space. So usually we wouldn't expect topological edge modes to be affected by even this atomically disordered step edge. And this is something what we generally see. This edge mode continues along this step edge, irrespective of these atomic defects. And if we go away from the superconducting state, for example, here we apply a high magnetic field out of plane, so the entire surface becomes normal. But there is no special features that can be associated with the step edge, again indicating that the enhancement of the zero biased conductance that we saw on the step edge occurs is something really deeply related to the superconducting state alone and does not appear in the normal state of this material. Now we saw so far that if we have a 1H step edge, we have an edge mode associated with it. And the next question we can ask is what happens when we have 1T as well above it and the step edge associated with this 1T layer. So for that, we'll look at some region like this. Here we have the 1T layer above, and we have the 1H layer below, which is exposed through this crater in the 1T layer. Now we take a DIDV map at zero energy with a finite magnetic field out of plane just to see how the vortex ordering look like. And we see something, an interesting feature here. We have this vortex which seems to be right at the edge of this 1T step edge. So let's zoom into this region where we saw this single vortex. So here the false color is the DIDV at, that is density of states at the zero energy. And we have the 1T above and the 1H layer below. And we see that there is this vortex which is partially exposed through this 1H layer, which what it really tells us is this entire 1H layer is superconducting, even though this top 1T layer might be slightly metallic. And this so this confirms that we have the 1H layer is superconducting throughout, even if it has this metallic 1T above. Now we want to examine what happens really at this edge of this 1T. So for that, let's look at this region, which has very well-defined step edges along two different directions. So this is shown here. The density of states at the zero bias is shown in the false color, overlaid on top of the topography. So we have the 1T above, which terminates at the step edge, and the 1H here. So we identify these two different directions, which are edge 1, which corresponds to one of the crystallographic directions, and edge 2, which actually corresponds to a CDW direction. And we see that interestingly, even before that there is some kind of enhancement in the zero bias conductance close to these 1T step edges. We can look at the profiles emanating from step edge 1 and step edge 2 to really quantify and compare how do they look like. And we see that the decay lengths of these two are slightly different. We have a smaller decay length for the edge 1 and a larger decay length of edge 2. Also note here, the edge 2 was the same edge direction that we saw for the 1H step edge. And irrespective of whether it's a 1H step edge or 1T step edge, as long as it is in the same direction, we get a similar decay length associated with this edge mode. And one can also imagine that, okay, maybe we have a metallic 1T above and therefore we get this enhancement, but that wouldn't explain why we have this anisotropy. And also we can track the position of the coherence peak, and we don't see any significant reduction or change of the position of the coherence peak as we approach this step edge. So strongly suggesting that there is indeed a special edge mode which is bound to this type of 1D edges. So what we see here is we have an edge mode at the 1H step edge and also an edge mode associated with the 1T step edge. So let me just summarize all the observations that we have seen so far. So one is we have two different types of step edges. So one is this a 1H step edge and 1T step edge. But before that, we had these point spectra, which showed this BCS-like, but the zero bias were higher than what we would expect from instrumental broadening. We measured this vortex lattice and do find a zero bias peak associated with this vortex, but this is not enough to distinguish the topological origin of it. And we see most remarkably this edge modes associated with 1H step edge and also the edge mode associated with the 1T step edge. Now, the fact that we see edge mode associated with the 1T step edge means that the topological phase has to be different here. So what we think is when we have a 1H superconductor, which is encapsulated by 1T above and below, we are in the trivial phase. And when it is not encapsulated by 1T above, we are in the topological phase. Therefore, across this topological phase domain, we have a boundary state associated with it. Now, let me briefly introduce this theoretical model that was done together in collaboration with Yuval and our other theoretical collaborators to explain all of our experimental observations on this material. So we start with this tantalum disulfur 1H lattice, where we see that different d orbitals play an important role at the Fermi energy. And this was one of the motivation to actually look into interorbital pairing in this system. So when we do DFT calculation of the 1H layer, we see that at the zero energy, or the Fermi energy, there are contributions from both the z square xy and the x square minus y square d orbitals. So let me denote this delta x, which is the pairing between the orbitals. This is the interorbital pairing term, and delta s, which would be the regular singlet pairing. Whenever we find this delta x, which is smaller than delta s, we are in the topology, we are in the trivial gap. But as we tune delta x and make it larger than delta s, we go across a topological phase transition, and we are left now with these certain nodal points in our brilliant zone, as shown here. And they have Dirac-like dispersion of these topological nodal points. And these nodal points are protected by mirror plus time reversal symmetry. Similar works have been done by other groups under different assumptions in different material conditions. But yes, whenever they find these topological nodal points, an interesting feature that appears is if we project it to edges, different edges will have different type of edge dispersion, similar to what you would imagine for graphene. So for example, on a certain edge, we can find a helical edge mode, and on some other edge, we can find flat Majorana bands associated with it. So we can compute the same thing for our band structure relevant to our band structure. So here is 1H tantalum disulfur, where we can compute these topological nodal points, which appear close to these band crossings. The presence of these topological nodal points also motivates us for using a finite offset whenever we do this BCS type fitting. Probably this is what gives rise to this zero bias conductance that cannot be explained by instrumental broadening. Now we project these nodal points to different edges. For example, if we project it to a zigzag edge, we find these helical Majorana modes associated with it crossing the zero energy. And if we project it to some arbitrary edge, then we can find these flat bands associated with it. But importantly, if we have edges which are somewhere between the zigzag and arbitrary, we can have a mixture of both dispersing helical Majorana edge modes and a combination of these flat bands. And this also means that if we look at the different edges, the localization length of this edge mode will also be different. This is exactly what we see along our two different edges that we have examined and shown earlier, that the different edges will have different localization. But now the question is, what gives rise to this topological phase? So this is where we realize that when we have 1T above and 1T above and below the 1H, then there is a strong charge transfer between the 1T layer and the 1H layer. But since they are symmetrically placed, the charge transfer, the electric dipole caused by it effectively cancels out. So there is the mirror symmetry out of plane for an encapsulated 1H layer is preserved. No spin orbit, Rashba type spin orbit coupling is also present here. But this places it in the trivial case. And we know that for interorbital pairing term, this delta X to appear, the mirror symmetry has to be broken. And this is exactly the case available when the 1H layer is exposed. So when it is exposed, we only have the 1T layer underneath it. And because of the strong charge transfer, we have an electric dipole across it. And that effectively breaks the mirror symmetry out of plane, giving rise to these Rashba type effects. And this is also what encourages delta X to be larger, the interorbital pairing term to be dominant, giving rise to these nodal points in the brilliant zone. And this actually neatly sums up our observation where we see edge mode associated with the 1H step edge. we have this edge mode also associated with the 1T step edge, because now we go from a topological phase in the superconducting 1H exposed layer to a trivial superconducting phase in a 1H encapsulated layer. So with this, I will conclude my presentation, and I'll just summarize here that we have this zero bias peak that we do find in this vortex core. But most importantly, we saw that there are edge mode associated with the step edges, both when there is a 1H step edge along arbitrary direction, or when there is 1T step edges along different directions, showing small anisotropy in the localization length of these edge modes. And we have this theoretical model of interorbital pairing, where we realize this topological superconductivity with nodal points. Thank you very much.
Thank you, Abhay. Are there any questions from the audience? It's kind of, I cannot see all of you, so maybe if you write your name in the chat and I can ask your question or just give you the permission to talk. Yeah, Elio, you can ask.
Hi, beautiful talk. So first, I didn't understand whether there is any trace of this putative spin liquid behavior left in this heterostructure or spect structure. And also, I didn't understand whether do I understand right that this is a two-dimensional topological superconductor envision, or are these hinge modes?
Right. So regarding your first question, where if there is any trace of quantum spin liquid, so what generally happens is when we place this 1H layer next to the 1T layer, because of the strong charge transfer from the 1T layer to the 1H layer, it also means that the moments which were localized on the CDW sites, they're also transferred to the 1H. So it could be interesting to examine what exactly they do. I don't think our current theoretical model, we don't really exactly know how it interacts. But definitely, this is something that we should consider, the spin moments which were now transferred from the 1T to the 1H sites. And also that the fact that we see this charge of 1T CDW on the 1H is a testament to that. Indeed, there is a strong charge transfer, and with the charge, there is a spin transfer. But we don't have a clear idea what it does, how it affects the superconductivity of 1H. And as for the second question, whether it's a hinge mode or not, so we are examining here basically as a 2D topological superconductor. And in that sense, we are talking, when we say this 1D edges, we are talking about the edges of the 2D system, the top layer system.
Thank you. Tammy?
Thank you for the question.
Yes, Abhay, thanks for the talk. Just a quick question. So on the right panel, we see these helical states, which coexist with bulk states. Do you think they're robust enough to actually see an experiment?
Just to make sure you're talking about these states?
Yeah. So in the panel just below, you can see that they coexist with bulk states, right?
Right, absolutely. So what we think is most of our signature appears from close to the gamma point. So we can think of this as at gamma, at this k equals 0, these states are far away from the bulk states. Just like you would imagine for wild systems, for example. So there are certain momentum regions where they are very well separated from bulk states, and that gives it the stability.
Okay, thanks.
Okay, Hadar Steinberg, hi Hadar.
Yes, hi, and
Hi.
my question is the importance of the charge transfer mechanism. So it looks like charge transfer is really important in changing the shape of the Fermi surface around the gamma point. And my question is, how important is that charge transfer comes specifically from the 1T tantalum sulfide? Suppose I can induce charge transfer placing the monolayer tantalum sulfide 1H on something else. Do you expect to see a similar effect, or is it 1T so important here?
Right, great. So there are two types of effects that were kind of discussed. One is the breaking of the mirror symmetry. And that would happen if you would indeed place it on any other substrate. But the other kind of also happens with the 1T layer is, along with the charge, there is also the spin, the localized spin of this 1T CDW sites that gets transferred. And as of now, I don't have a clear idea what this does. And this could be really the critical difference between what if we place it on 1T substrate, or if we place it on some other substrate, which would also break the mirror symmetry out of plane.
Okay, so last question, Yoichi, you want to ask it yourself?
Okay, yeah. So to interpret this zero bias peak seen by STM, I think we need to understand how many calories geometrical modes are expected within the gap. So what is the delta over EF ratio?
Right. So we think the Fermi energy here is much higher, 100 MeV or that order. So that clearly does not allow us to distinguish this from CDGM state. So from this zero bias peak, we really don't know what its origin is.
Okay, thank you.
Okay, thank you, Abhay. We all thank you for your talk. So let's continue to the next speaker.